Hello there, and welcome to the Sleepless Scientist. Tonight, we descend into a world that covers most of our planet, yet remains more mysterious than the surface of the moon. We're diving into the deep sea, a realm of eternal darkness, crushing pressure, and life forms so strange, they seem borrowed from science fiction. Below the surface of familiar waves lies an alien landscape of mountains taller than Everest, valleys deeper than any canyon on land, and creatures that create their own light in the endless night. This is a journey through layers of water, through zones of fading light, into abyssal plains where the rules of life are rewritten. So settle in, let your mind drift downward with us, past the surface, past the sunlight, into the quiet mystery of the deep. And just before we begin, if these calm, curious explorations help you unwind, or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. The story begins at the shore. Stand at the edge of the ocean. Feel the waves touch your feet. The water seems familiar here. Clear, warm, alive with motion. You can see the sand beneath the surface. You can watch fish darting through shallow water, seabirds dive for prey. The sun glints off every ripple. This is the ocean we know, the ocean of beaches and boats and summer days. But this is only the beginning. Step deeper, wade out until the water reaches your chest. Look down. Already the bottom is harder to see. The light penetrates, but it's softer now, filtered through layers of water. Go deeper still. Swim out, beyond the breaking waves. The bottom disappears. You're floating above something vast. Beneath you, the seafloor drops away. 10 feet, 20, 100, 1,000. The shallow familiarity gives way to mystery. The ocean we know from shore is just a thin film on the surface of something immense. Most of Earth's ocean lies in darkness, in cold, in depths we rarely think about. Tonight, we follow that descent. We trace the path from light to dark, from familiar to alien. The story begins at the shore, but the ocean's true nature reveals itself only when we venture into the deep, the ocean that covers our world. Look at Earth from space. You see blue, so much blue. Oceans cover about 71% of our planet's surface. That's nearly 3/4 of everything. Land is the exception. Water is the rule. These oceans hold about 1.335 billion cubic kilometers of water. The number is almost meaningless. It's too large to grasp. But think of it this way. If you could collect all Earth's water into a sphere, it would be about 1,400 kilometers across. That sphere would dwarf most moons in our solar system. The ocean connects everything. The Pacific, Atlantic, Indian, Southern, and Arctic oceans are all one continuous body of water. A drop of water in the Arctic could eventually drift to the coast of Australia. Currents circulate through all of them, carrying heat, nutrients, and life across the globe. The ocean regulates Earth's climate. It absorbs heat from the sun and distributes it around the planet. It produces more than half the oxygen we breathe through the photosynthesis of phytoplankton. Without the ocean, Earth would be unrecognizable. It would be a barren, extreme world of temperature swings and thin air. The ocean is not just a feature of Earth. It is Earth's defining characteristic, and most of it, the vast majority, lies in the deep. How deep the sea truly is. The average depth of the ocean is about 3,688 meters. That's roughly 12,100 feet, or just over 2 miles. But averages hide extremes. In some places, the ocean is shallow, just a few dozen feet deep. In others, it plunges to depths that dwarf mountains. The deepest point on Earth is the Challenger, deep in the Mariana Trench, nearly 11,000 meters down. That's almost 7 miles below the surface. If you placed Mount Everest at the bottom of the Challenger Deep, its peak would still be over a mile underwater. The ocean's depth is difficult to comprehend from the surface. When you look at the sea, you see only a flat expanse, but beneath that surface lies volume, immense three-dimensional space filled with water. Most of this volume is deep water. Most of the ocean exists below 1,000 meters, in perpetual darkness. We live on the surface of a water world, yet we know more about the surface of Mars than we do about the deep sea. Only a tiny fraction of the ocean floor has been mapped in detail. Most remains unexplored, unseen, unknown. The deep sea is Earth's last true frontier, and it holds secrets we're only beginning to uncover. The layers beneath the waves. The ocean is not uniform. It's divided into layers, each with its own character. Scientists organize these layers by depth and light. The sunlight zone, or epelagic zone, extends from the surface to about 200 meters down. This is where most familiar marine life exists. Sunlight penetrates. Photosynthesis occurs. Below that lies the twilight zone, or mesopelagic zone, from 200 to 1,000 meters. Here, light fades. Only the faintest blue glow reaches this depth. Deeper still is the midnight zone, or bathypelagic zone, from 1,000 to 4,000 meters. No sunlight reaches here. Darkness is total. Pressure is immense. Yet, life persists. Below the midnight zone lies the abyssal zone, from 4,000 to 6,000 meters. This is the realm of the abyssal plains, vast, flat expanses of ocean floor covered in fine sediment. And finally, the Hadal zone, from 6,000 meters to the deepest trenches. This is the least explored, most extreme environment on Earth. Each layer presents unique challenges to life. Temperature drops, pressure increases, light vanishes, food becomes scarce. Yet in each layer, life has found a way. The layers of the ocean are like worlds stacked upon worlds, each more alien than the last. The sunlit surface of life. The surface of the ocean is alive. Phytoplankton drift in vast blooms, turning the water green. They're microscopic plants, the foundation of the ocean's food web. They photosynthesize, converting sunlight into energy, producing oxygen as a byproduct. Fish of every size swim through these waters. Tuna, mackerel, herring, sardines, dolphins leap, sharks patrol, sea turtles glide. This is the ocean we see in documentaries, the ocean of abundance and color. Coral reefs exist here, in shallow tropical waters, where sunlight reaches the bottom. These reefs are cities of life, home to thousands of species. Kelp forests sway in temperate shallows, providing shelter and food. The sunlit zone is warm. In tropical regions, surface temperatures can reach 30 degrees Celsius or more. Even in cooler regions, the surface is warmer than the depths below. Sunlight is energy. Energy sustains life, and so the surface teems with it. But this abundance is fragile. It depends on sunlight, which can only penetrate so far. Below 200 meters, photosynthesis becomes impossible. The food produced at the surface must drift downward or be carried by migrating creatures. The sunlit surface feeds the deep. Without it, the darkness below would be even more barren. The twilight zone begins. Descend past 200 meters. The light changes. Blue becomes deeper, darker. Shadows disappear because there's not enough light to cast them. You're entering the twilight zone. This is the mesopelagic layer, where faint sunlight still penetrates, but cannot sustain photosynthesis. The water here is cooler, the pressure is higher, and life begins to change. Many creatures here have large eyes adapted to capture every trace of light. Others are bioluminescent, producing their own glow. During the day, many animals hide in the twilight zone, avoiding predators in the bright surface waters. At night, they rise. This is called diel vertical migration, and it's one of the largest movements of biomass on Earth. Billions of fish, squid, and crustaceans travel hundreds of meters up and down every day. The twilight zone is a world of transition. It's neither surface nor abyss, but something between. Light exists here, but barely. Food is less abundant than at the surface, but more common than in the darkness below. Creatures here must be efficient, adaptable, patient. This zone is vast. It contains more fish than any other part of the ocean, yet we know relatively little about it. Most of its inhabitants remain unidentified. The twilight fades, and below, the true deep begins. The world where light fades away. There's a moment, as you descend through the twilight zone, when the last trace of sunlight disappears. You've reached a depth where looking up reveals no hint of the surface. The world above is gone. The faintest shimmer of light fades into absolute darkness. This transition happens around 1,000 meters. Below this depth, sunlight never reaches. Even on the brightest day, even in the clearest water, the deep remains dark. This is not the darkness of a moonless night. You can adapt to night. Your eyes adjust. Shapes emerge. But in the deep sea, there is nothing to adjust to. Without a light source, you see nothing, ever. This is the environment where most of the ocean exists. Darkness, eternal darkness, and yet life persists. In the absence of light, creatures have evolved extraordinary adaptations. Some navigate by sensing vibrations in the water. Others rely on chemical signals. Many produce their own light through bioluminescence. The world where light fades away is not lifeless. It's different, alien, a place where the rules of surface life no longer apply. Here, the deep truly begins. The midnight zone of eternal darkness. Welcome to the bathypelagic zone, the midnight zone, from 1,000 to 4,000 meters deep. This is the realm of perpetual night. No sunlight, no photosynthesis, no plants. The temperature here hovers just above freezing, around 2 to 4 degrees Celsius. The pressure is crushing, hundreds of times greater than at the surface. Food is scarce. Most organic matter from the surface is consumed before it reaches this depth. What does arrive is called marine snow, a slow drift of dead plankton, fecal matter, and organic debris sinking from above. Creatures here feed on marine snow, on each other, or on the rare carcass of a whale or large fish that sinks from the surface. Life is sparse. Fish are small, with slow metabolisms. They conserve energy. They wait. Many have enormous mouths relative to their body size, allowing them to eat prey larger than themselves. You never know when your next meal will come. The midnight zone is silent. Sound travels well in water, but there's little to make sound. No wind, no rain, just the occasional movement of a creature through the dark. This is the deep as most people imagine it. Cold, dark, empty, hostile. And yet even here, life finds a way. Pressure beyond imagination. At the surface, atmospheric pressure is about 1 bar. That's the weight of the air above us. Descend into the ocean, and pressure increases by roughly 1 bar for every 10 meters. At 100 meters, the pressure is 11 bars. At 1,000 meters, it's 101 bars. At the bottom of the Mariana Trench, nearly 11,000 meters down, the pressure exceeds 1,000 bars. That's more than 15,000 pounds per square inch. If you took an empty aluminum can to the bottom of the trench, it would be crushed into a tiny solid lump. A human body, unprotected, would be destroyed instantly. Pressure at those depths compresses everything, yet deep-sea creatures thrive in it. How? They've evolved bodies without air spaces. No lungs filled with gas, no swim bladders. Their cells are filled with fluids and solids that are incompressible. The pressure outside equals the pressure inside. They feel no crushing force. To them, the pressure is normal. Bring a deep-sea creature to the surface, and it suffers. The sudden drop in pressure causes gases to expand, tissues rupture. Some creatures brought up from the deep arrive as gelatinous blobs, their bodies destroyed by decompression. Pressure shapes life in the deep. It limits what can survive, and it creates a world we can barely visit. The silence of the deep. The deep sea is quiet, profoundly quiet. There are no waves crashing, no wind howling, No seabirds calling. Sound exists, but it's sparse and strange. A distant hum of geological activity. The faint clicks and calls of whales miles away. The rare movement of a predator. Sound travels exceptionally well in water, much better than in air. A whale's song can travel hundreds of miles through the ocean. Yet in the deep, most creatures make little noise. They have no reason to. Many lack vocal structures. Fish don't have vocal cords. Some produce sounds by grinding teeth or vibrating swim bladders. But in the deep, these adaptations are rare. Silence is a form of camouflage. In darkness, sound can give you away. So creatures move quietly. They drift. They wait. The silence of the deep is not empty. It's full of tension. It's the quiet of a predator, waiting in ambush. The quiet of prey, holding perfectly still. In the absence of light and sound, other senses take over. Creatures detect vibrations, chemical signals, electrical fields. The deep sea is a world of whispers, and in the silence life listens. The coldest waters on Earth. Below 1,000 meters, the ocean is cold. Temperatures hover between 2 and 4 degrees Celsius. In polar regions, deep water can drop below zero without freezing due to salt content and pressure. The cold is constant. There are no seasons in the deep. No summer warming, no winter chill, just eternal cold. This cold slows everything. Chemical reactions occur more slowly. Metabolism slow, growth slows. Deep sea creatures often live much longer than their shallow water relatives. A Greenland shark, living in the cold depths of the Arctic, can live over 400 years. The orange roughy, a deep sea fish, can live over 150 years. Cold water holds more dissolved oxygen than warm water, which is beneficial for life. But cold also demands efficiency. Creatures in the deep cannot afford to waste energy generating heat. Most are cold-blooded, their body temperatures matching the surrounding water. The cold shapes behavior. Movements are slow and deliberate. Reproduction is infrequent. Development takes time. A single egg might take months or years to hatch. The coldest waters on Earth are home to some of the oldest, slowest, most patient creatures alive. They live in a world where time passes differently. Creatures of the abyss. Imagine creatures adapted to a world we can barely survive in. Fish with fangs longer than their bodies. Squid with eyes the size of dinner plates. Shrimp glowing with bioluminescent bacteria. Worms living on chemical energy. The creatures of the abyss are strange beyond expectation. Many are small. Food is scarce, so large bodies are inefficient, but some are enormous. The giant squid, the colossal squid, the giant isopod. These are exceptions, giants thriving in the deep. Most deep-sea creatures are black or red. In the absence of light, coloration doesn't matter for communication. Black absorbs any stray bioluminescence, making creatures invisible. Red appears black in the deep because red light doesn't penetrate water. Many creatures are gelatinous. Solid muscles and bones require energy to maintain. In the deep, where food is scarce, a gelatinous body is more efficient. Some creatures have transparent bodies, rendering them nearly invisible. Others have photophores, light-producing organs, arranged across their bodies in species-specific patterns. These lights serve as communication, camouflage, or lures. The creatures of the abyss are not mistakes or monsters. They're masterpieces of adaptation, each one perfectly suited to its world. The strange glow of bioluminescence. In the darkness of the deep, light exists. Not sunlight, but a different kind of light. A glow produced by living creatures. This is bioluminescence, and it's one of the most common adaptations in the deep sea. Estimates suggest that up to 90% of deep-sea creatures produce light in some way. The light is usually blue or green. These wavelengths travel farthest in water. The glow is soft, eerie, beautiful. A jellyfish pulses with blue light. A squid flashes patterns across its body. An anglerfish dangles a glowing lure. Bioluminescence serves many purposes. It attracts prey, it confuses predators, it helps individuals find mates in the vast darkness. Some creatures use it as camouflage. By producing light on their undersides that matches the faint glow from above, they erase their silhouette. This is called counter-illumination. In the deep, light is a tool. It's a weapon. It's a language. Creatures blink messages to each other in patterns we're only beginning to understand. The strange glow of bioluminescence transforms the deep from a world of darkness into a world of hidden light. Faint, fleeting, but there. How animals create their own light. Bioluminescence is a chemical reaction. Inside specialized cells called photophores, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase. The reaction releases energy in the form of light. It's remarkably efficient. Almost no energy is wasted as heat. Some creatures produce luciferin themselves. Others obtain it from their diet or from symbiotic bacteria living in their bodies. The Hawaiian bobtail squid, for example, harbors colonies of glowing bacteria in a specialized organ. The squid controls when the bacteria glow, using their light for camouflage. Bioluminescence evolved independently many times in different lineages. It's a convergent solution to the problem of living in darkness. The chemical mechanisms vary, but the result is always the same: light from life. Humans have harnessed bioluminescence for research in medicine. Luciferase is used as a marker in genetic studies, allowing scientists to track genes by watching them glow. The glow of the deep sea has illuminated our understanding of biology itself. How animals create their own light is a story of chemistry, evolution, and ingenuity. It's a reminder that life finds solutions to even the most challenging problems. The hunters of the dark. In the deep, predation is an art of patience. Food is scarce. Energy is precious. Predators cannot afford to chase prey across long distances. Instead, they wait, they lure, they ambush. Many deep-sea predators have enormous mouths. The gulper eel has a mouth that can open wide enough to swallow prey larger than itself. Its jaw is unhinged, its stomach expandable. It doesn't know when it will eat again, so it must take advantage of every opportunity. Other predators use bioluminescence to lure prey. The anglerfish is the most famous example, but many creatures employ similar strategies. They dangle glowing lures, attracting curious fish or squid. When prey comes close, they strike. Some predators are ambush hunters. The viperfish has teeth so long it cannot close its mouth. It hovers motionless in the water, waiting for prey to swim near. Then, in a burst of speed, it impales its victim. Deep-sea predators are efficient killing machines. They've evolved to make the most of every encounter. Every calorie counts. In the darkness, the hunters of the deep are invisible until the moment they strike, and by then, it's too late. The lanternfish and its secret world. The lanternfish is one of the most abundant vertebrates on Earth. You've probably never heard of it. These small fish, usually just a few inches long, live in the twilight and midnight zones. They have rows of photophores along their bodies, glowing softly in the dark. During the day, they descend to depths of 300 to 1,000 meters, hiding from predators. At night, they rise to the surface to feed on plankton. This daily migration is called dull vertical migration, and lanternfish are its champions. Billions of them move up and down every day. The collective biomass is staggering. Some estimates suggest that lanternfish make up as much as 65% of all deep-sea fish biomass. They're a crucial link in the ocean's food web. They consume plankton at the surface and carry that energy into the deep, where they become prey for larger fish, squid, and marine mammals. The lanternfish's secret world is vast and hidden. They live in numbers so large we can barely comprehend them, yet most people will never see one. They're a reminder that the most abundant creatures on Earth often live far from human eyes. The enigmatic anglerfish. Picture this: a fish with a fishing rod growing from its head. At the end of the rod, a glowing lure. The anglerfish is one of the most iconic creatures of the deep. There are many species, each with unique adaptations, but all share the same strategy. They lure prey with light. The fishing rod is actually a modified dorsal spine called an esca. At its tip, bioluminescent bacteria glow. The anglerfish waves the lure back and forth, attracting curious fish or squid. When prey comes close enough, the anglerfish strikes. Its mouth is enormous, its teeth pointed inward. Prey cannot escape. Here's something stranger. In many anglerfish species, sexual dimorphism is extreme. Females are large, up to a meter long in some species. Males are tiny, sometimes just a few centimeters. When a male finds a female, he bites into her body and fuses with her. His tissues merge with hers. He becomes a parasitic appendage, losing his eyes, fins, and most internal organs. He exists only to fertilize her eggs. The anglerfish is enigmatic, bizarre, and perfectly adapted to the deep. It's a creature that challenges our assumptions about how life should look. The vampire squid from hell. Despite its name, the vampire squid is not a true squid, nor does it drink blood. It's a cephalopod in its own order, Vampiromorphida. It lives in oxygen minimum zones at depths of 600 to 900 meters, where oxygen levels are so low that most creatures cannot survive. The vampire squid is small, about the size of a football. Its body is covered in light-producing photophores. When threatened, it can flash bright bioluminescent clouds to confuse predators. It has large blue eyes relative to its body size, the largest eye-to-body ratio of any animal. Its 8 arms are connected by a web of skin. When threatened, it pulls this web over its body, creating a defensive cloak. Inside the cloak, fleshy spines protrude, deterring predators. The vampire squid feeds on marine snow, dead plankton, and organic debris drifting down from above. It uses long, sticky filaments to collect the particles, then retracts the filaments and wipes the food into its mouth. It's a gentle scavenger, not a fearsome predator. The name vampire squid from hell was given due to its appearance: dark red, web-armed, with glowing eyes. But the reality is far less sinister. It's a shy, slow-moving creature, perfectly adapted to low-oxygen environments. Transparent and ghostly creatures. Some creatures of the deep are nearly invisible. Their bodies are transparent, allowing light, what little exists, to pass through. This transparency is a form of camouflage. In the twilight zone, where faint light filters down, being invisible is an advantage. Transparent jellyfish drift like ghosts. Their bells are clear, their tentacles shimmer faintly. You can see through their bodies to the water beyond. Glass squid, barrel-eye fish, and transparent sea cucumbers all employ this strategy. The barrel-eye fish is particularly strange. Its head is transparent, filled with fluid. Its tubular eyes point upward, looking through its own skull to spot prey silhouetted against the faint light above. Transparency requires specific body chemistry. Proteins in muscle and tissue must be arranged to minimize light scattering. Red blood must be replaced with clear fluids or made transparent. It's a complex adaptation, but in the twilight zone, it works. These ghostly creatures move through the water unseen, hunting or avoiding predators. They're reminders that survival in the deep requires creativity. Evolution finds solutions that seem impossible, and in the ocean's twilight, the impossible becomes real. The life that drifts with the currents. Not all deep-sea creatures swim actively. Many drift. They float with the currents, conserving energy, letting the ocean carry them. This lifestyle is called planktonic. Plankton are not a single group of organisms. The term refers to any creature that drifts, rather than swims. Phytoplankton are microscopic plants. Zooplankton are animals, ranging from tiny copepods to large jellyfish. In the deep, planktonic life includes salps, siphonophores, and larval stages of many fish and invertebrates. These drifting creatures form vast, invisible clouds of life. Drifting is efficient. Swimming requires energy. In the deep, where food is scarce, conserving energy is crucial. By drifting, creatures can cover large areas without expending effort. Currents carry them through feeding grounds. Some plankton migrate vertically, rising at night to feed at the surface, sinking during the day to avoid predators. The life that drifts is often delicate. Gelatinous bodies, thin tissues. These creatures are fragile, but successful. They've existed for hundreds of millions of years. Drifting is not passive, it's a strategy. And in the vastness of the deep, it works. The dance of plankton. Plankton seem insignificant, microscopic, invisible to the naked eye. But together, they're the foundation of the ocean's food web. Phytoplankton are single-celled plants that float near the surface, photosynthesizing. They produce about half the oxygen on Earth, more than all the forests combined. Zooplankton are tiny animals, copepods, krill, larval fish, that feed on phytoplankton. They, in turn, are eaten by larger animals. A single drop of seawater can contain millions of plankton. In bloom conditions, phytoplankton turn vast areas of ocean green or red. These blooms are visible from space. They feed the entire marine ecosystem. Without plankton, there would be no fish, no whales, no seals, no seabirds. The entire ocean would collapse. The dance of plankton is a cycle. Phytoplankton photosynthesize. Zooplankton graze on them. Larger creatures eat zooplankton. Waste and dead matter sink into the deep, feeding creatures below. The cycle connects surface to abyss. It's a dance of life and death, energy and matter, repeated endlessly across the ocean. Plankton may be small, but their impact is immeasurable. The beauty of jellyfish. Jellyfish drift through the deep like living lanterns. Their bells pulse rhythmically. Their tentacles trail behind, sometimes stretching dozens of feet. Many deep-sea jellyfish are bioluminescent, glowing with soft blues, greens, and reds. They're among the most beautiful creatures in the ocean. Jellyfish are ancient. They've existed for over 500 million years, predating fish, dinosaurs, and humans. They're simple organisms. No brain, no heart, no bones, just a bell of gelatinous tissue and a mouth surrounded by tentacles. Despite their simplicity, they're effective predators. Tentacles are armed with nematocysts, stinging cells that inject toxins into prey. A small fish brushing against a tentacle is paralyzed instantly. Deep-sea jellyfish feed on plankton, small fish, and sometimes other jellyfish. They drift with currents, pulsing gently to maintain position or move toward prey. Some species can survive in the deepest trenches. Others bloom in massive numbers, their populations exploding under the right conditions. Jellyfish are fragile. Their bodies are over 95% water, yet they're survivors. They thrive in environments where other creatures struggle. The beauty of jellyfish is ethereal, alien, a reminder that life can be both simple and exquisite. The architects of coral reefs. Coral reefs exist in shallow, sunlit waters. Not in the deep, but deep-sea corals do exist, building structures in the dark. These cold-water corals live at depths from 200 to over 3,000 meters. They don't rely on photosynthesis. Instead, they filter feed, capturing plankton and organic particles from the water. Deep-sea corals grow incredibly slowly. Some species add less than a millimeter per year. A coral reef in the deep might be thousands of years old. These ancient structures provide habitat for fish, crustaceans, and other invertebrates. They're oases of life in the barren abyss. Coral reefs, both shallow and deep, are architects of ecosystems. They build three-dimensional structures that increase habitat complexity. Crevices, overhangs, and branches provide shelter and feeding grounds. In the deep, where the ocean floor is often flat and featureless. Coral structures attract life. Deep-sea corals are vulnerable. They grow slowly, so damage is nearly impossible to reverse. Bottom trawling, dragging nets across the seafloor, destroys coral reefs that took millennia to form. Protecting these structures is essential. They're not just beautiful, they're irreplaceable. The architects of coral reefs, both shallow and deep, build cities for the ocean's inhabitants. The ocean floor beneath it all. Below the water column, beneath the drifting plankton and swimming fish, lies the ocean floor. Vast, varied, mostly unexplored. The seafloor is not uniform. It's a landscape of mountains, valleys, plains, and trenches. In some places, it's covered in soft sediment, fine mud, and clay that has settled over millions of years. In others, it's rocky, volcanic, jagged. The ocean floor is Earth's largest habitat. It covers more area than all the continents combined. Yet we've mapped less than 20% of it in detail. Most remains unseen. The floor is not lifeless. Creatures crawl across the sediment. Worms burrow into the mud. Sea cucumbers vacuum up organic matter. Brittle stars cling to rocks. Even in the deepest trenches, life exists. The ocean floor is ancient. Some of the sediment is millions of years old. It contains a record of Earth's history, layers of dust, volcanic ash, and the shells of countless microscopic organisms. Scientists drill into the seafloor to extract cores, reading the planet's past. The floor beneath it all is the foundation of the ocean, and like the water above, it holds mysteries we're only beginning to explore. Mountains and valleys below the sea. The ocean floor is not flat, it's mountainous. The mid-ocean ridge system is the longest mountain range on Earth, stretching over 65,000 kilometers. These underwater mountains are volcanic, formed by tectonic activity. Magma rises from the mantle, creating new crust. The ridges mark the boundaries between tectonic plates. Valleys called rift valleys run along the crests. In some places, seamounts, underwater mountains that don't reach the surface, rise thousands of meters from the seafloor. Some seamounts are extinct volcanoes. Others are still active. These mountains create habitats for deep-sea life. Currents flow over and around them, carrying nutrients. Fish gather, corals grow. There are also submarine canyons, deep, steep-sided valleys carved into the continental shelf. These canyons funnel sediment and organic material from shallow waters into the deep, creating highways for nutrients. The Monterey Canyon off California rivals the Grand Canyon in size and depth. Mountains and valleys below the sea create diversity. They shape currents, influence ecosystems, and provide structure in an otherwise flat abyss. They're reminders that the ocean floor is as dynamic and varied as the land we walk on. The vast abyssal plains, below 4,000 meters, lies the abyssal zone. Here, the ocean floor flattens into vast plains. These abyssal plains cover more area than any other habitat on Earth. They're featureless, flat, covered in layers of fine sediment, mud, clay, and the remains of microscopic organisms. The sediment is soft. If you could walk on it, your feet would sink. The plains are among the most uniform environments on the planet. Temperature is constant. Pressure is constant. Light is absent. Yet even here, life exists. Creatures burrow into the sediment. Worms, clams, crustaceans. Others crawl across the surface. Sea cucumbers, brittle stars, tripod fish. Tripod fish are remarkable. They have elongated fins that act as stilts, allowing them to stand on the sediment and face into the current, catching drifting particles. The abyssal plains are silent. Still, the currents here are slow. Water moves at just a few centimeters per hour. Food is scarce. Most organisms are small and slow-growing. Life in the abyssal plains is patient. Time moves differently here. A single worm might take decades to mature. The vast abyssal plains remind us that life doesn't require abundance or variety. It requires only persistence. The deepest trenches on Earth. Beyond the abyssal plains, the ocean floor drops away into trenches. These are the deepest places on Earth. Trenches form where one tectonic plate is forced beneath another in a process called subduction. The descending plate creates a deep, narrow trench in the seafloor. There are several major trenches: the Peru-Chile Trench, the Japan Trench, the Tonga Trench. But the deepest is the Mariana Trench in the Western Pacific. The trenches are extreme environments. Pressure exceeds 1,000 bars. Temperatures are near freezing. Food is almost non-existent. Yet life has been found in every trench explored. Amphipods, small shrimp-like crustaceans, thrive in the trenches. Some species grow to enormous sizes. Fish called snailfish have been found at depths over 8,000 meters. The deepest trenches represent the final frontier of the ocean. They're the least accessible places on our planet. Only a handful of human expeditions have reached them. The trenches challenge our understanding of life's limits. They show that even in the most extreme conditions, life persists. The deepest trenches on Earth are windows into the absolute edge of possibility. The Mariana Trench, world's deepest place. The Mariana Trench lies in the western Pacific Ocean, east of the Mariana Islands. Its deepest point, the Challenger Deep, plunges to nearly 11,000 meters below sea level. That's deeper than Mount Everest is tall. If you placed Everest at the bottom, its peak would still be more than a mile underwater. The trench is a crescent-shaped scar in the seafloor, over 2,500 kilometers long, but only about 69 kilometers wide. The pressure at the bottom is crushing, over 1,000 times atmospheric pressure at sea level. In 1960, two men descended to the Challenger deep in a bathyscaphe called the Trieste. They saw fish. They saw shrimp. Life existed even there. In 2012, filmmaker James Cameron made a solo descent. He collected samples and recorded video. Scientists have sent robotic landers into the trench. They've discovered amphipods, sea cucumbers, and microbial life. The Mariana Trench is not lifeless. It's not empty. It's a thriving ecosystem at the edge of possibility. The trench is a reminder of Earth's vastness. We often think of our planet as mapped and known, but the deepest place on Earth remains largely unexplored. The pressure at the bottom of the world. At the bottom of the Mariana Trench, the pressure is about 1,086 bars. That's roughly 15,750 pounds per square inch. Imagine the weight of 50 jumbo jets balanced on your thumbnail. That's the pressure at the bottom of the world. Human bodies cannot withstand it. Unprotected, you'd be crushed instantly. Your lungs would collapse. Your bones would compress. Yet creatures living there feel nothing unusual. Their bodies have no air spaces. Their tissues are filled with incompressible fluids. The pressure outside equals the pressure inside. They're perfectly adapted. Submarines that descend to the trench must be built like tanks, thick steel or titanium spheres. Even then, the metal groans under the strain. Small imperfections can become catastrophic failures. The pressure at the bottom of the world shapes everything. It determines what materials can survive. It limits human access. It creates an environment so extreme that exploring it is harder than going to space. In space, the pressure difference is just 1 atmosphere. In the trench, it's over 1,000. The bottom of the world is closer than the moon, yet far more difficult to reach. What lives 7 miles below? 7 miles below the surface. In the Haddle Zone, life exists in forms adapted to extremes. Snailfish are among the deepest living vertebrates. They're gelatinous, with soft bones and translucent skin. They feed on small crustaceans and amphipods. Amphipods are everywhere in the trenches. These small shrimp-like creatures scavenge organic matter. Some species have adapted to eating wood and bone that sinks from the surface. Giant amphipods, some reaching over 30 centimeters long, prowl the trench floor. Sea cucumbers crawl through the sediment, vacuum feeding on organic particles. Microbial life thrives in the sediment and in the water column. These bacteria and archaea metabolize chemicals and organic matter. They're the foundation of the trench food web. What lives 7 miles below is tough, efficient, patient. These creatures grow slowly, reproduce infrequently, and live long lives. They represent life, stripped to its essentials. No color, no light, just survival. Yet they're successful. They've colonized the deepest places on Earth. They remind us that life is not fragile. It's tenacious. It pushes into every possible niche. Even 7 miles below, the snailfish of the abyss. Snailfish are remarkable. They hold the record for the deepest living fish ever recorded. In 2017, scientists captured footage of a snailfish at 8,178 meters in the Mariana Trench. These fish are unlike any surface species. Their bodies are soft, almost gelatinous. They lack scales. Their bones are thin and flexible, not rigid. Their bodies are mostly water and cartilage. This adaptation allows them to withstand immense pressure. Snailfish are small, usually less than 30 centimeters long. They're pale or translucent. They have small eyes. Vision is less important in the darkness. They feed on small invertebrates, particularly amphipods. Despite living in one of Earth's harshest environments, snailfish are successful. There are hundreds of species, most living in deep water. The snailfish of the abyss are proof that vertebrates can adapt to extreme depths. They're not monsters. They're small, soft, unremarkable-looking fish. Yet they've conquered an environment that kills most other life. Their success is a testament to evolution's creativity. Life finds a way, even at the very edge. Creatures that thrive in darkness. Darkness is not an obstacle. It's an environment, and creatures have adapted to thrive in it. Without vision as the primary sense, deep-sea creatures rely on other methods. Many have highly developed lateral lines, organs that detect vibrations and pressure changes in water. They feel movement. Electroreception is common. Some fish can detect the faint electrical fields generated by muscle contractions. This allows them to sense prey in complete darkness. Chemoreception, the ability to detect chemicals in water, is crucial. Creatures follow scent trails to find food, mates, and avoid predators. Bioluminescence serves as both a tool and a language. Creatures communicate, hunt, and navigate using light they create. The darkness of the deep is not empty. It's full of information, vibrations, chemicals, electrical signals, faint glows. Creatures that thrive in darkness have learned to read these signals. They've traded eyes for other senses. They've adapted their entire sensory systems, and in doing so, they've unlocked an environment that covers most of the planet. Darkness is not a limitation. For deep-sea life, it's home. The power of adaptation. Adaptation is evolution's answer to challenge. In the deep sea, challenges are extreme. No light, little food, crushing pressure, near freezing temperatures. Yet life has adapted to all of it. Consider the gulper eel. Its mouth is enormous, capable of swallowing prey larger than itself. Its stomach expands to accommodate large meals. Why? Because food is rare. When an opportunity comes, you must take it. Consider the barrel-eye fish. Its eyes are tubular, pointing upward, encased in a transparent head. Why? To see the silhouettes of prey against the faint light above, while remaining hidden below. Consider the vampire squid. It lives in oxygen minimum zones, where most creatures suffocate. Its blood contains hemocyanin, a copper-based molecule, more efficient than hemoglobin at binding oxygen in low oxygen environments. Every adaptation is a solution. Every strange feature has a purpose. The deep sea has pushed life to evolve in ways unimaginable at the surface. The power of adaptation is that it has no limits. Given time and pressure, life reshapes itself. It becomes whatever it needs to be to survive. And in the deep, life has become extraordinary. How life survives without sunlight. Sunlight is the foundation of most ecosystems. Plants photosynthesize. Herbivores eat plants. Carnivores eat herbivores. Energy flows from the sun. But in the deep sea, sunlight doesn't reach. So how does life survive? The answer is twofold. First, organic matter drifts down from above. Marine snow, dead plankton, feces, dead fish, sinks slowly into the depths. This provides food. It's not much, but it's enough. Scavengers feed on it. Predators feed on the scavengers. The energy that originated at the surface eventually reaches the deep. Second, some ecosystems in the deep don't rely on sunlight at all. They rely on chemosynthesis at hydrothermal vents and cold seeps. Chemicals from Earth's interior provide energy. Bacteria convert these chemicals into organic matter. Other creatures feed on the bacteria. These ecosystems are entirely independent of the sun. They're powered by geology, not astronomy. Life in the deep shows that sunlight, while important, is not essential. Life can find other sources of energy. It can tap into chemical reactions. It can scavenge. It can adapt. How life survives without sunlight is a testament to resilience and creativity. The hydrothermal vents. In 1977, scientists exploring the Galapagos Rift made a discovery that changed biology. They found hydrothermal vents, fissures in the seafloor, spewing superheated water. Around these vents, life thrived, not scattered individuals, but dense communities. Giant tube worms, clams, mussels, crabs, fish, all clustered around the vents. This was unexpected. The vents are extreme environments. Water temperatures reach 400 degrees Celsius. The water is acidic, full of toxic chemicals like hydrogen sulfide. Yet life was abundant. How? The answer is chemosynthesis. Bacteria living around the vents convert chemicals hydrogen sulfide, methane, into organic matter. They use chemical energy instead of sunlight. These bacteria form the base of the vent food web. Tube worms have no mouths or digestive systems. They house chemosynthetic bacteria in their tissues. The bacteria produce food. The worms provide shelter. It's a symbiotic relationship. Hydrothermal vents are oases in the deep. They're rare, scattered along mid-ocean ridges. But where they exist, they support ecosystems, unlike any other on Earth. The discovery of vents showed that life doesn't need the sun. It needs only energy, and energy can come from many sources. The chimneys of the deep. Hydrothermal vents often form structures called chimneys, as superheated water, rich in dissolved minerals, erupts from the seafloor. It meets cold seawater. The minerals precipitate out, building up over time. The result is a chimney, a tall, narrow structure made of metal sulfides. Some chimneys grow to tens of meters tall. They're fragile, made of brittle mineral deposits, but they're also active. Water pours from their tops at temperatures exceeding 400 degrees Celsius. The water is black, filled with suspended particles. These are called black smokers. Other vents produce cooler water, around 250 degrees, rich in different minerals. The water appears white. These are white smokers. The chimneys of the deep are geological features, but they're also biological hotspots. Creatures cluster around them, feeding on the chemicals and bacteria. Barnacles, limpets, crabs, and fish swarm the base. Tube worms attach to the sides. The chimneys are islands of life in an otherwise barren seafloor. They're temporary. Vents can shut off when tectonic shifts close the fissures. When that happens, the community collapses. But new vents open elsewhere, and life migrates, colonizes, and thrives once more. Life that feeds on chemicals, not light. Chemosynthesis is the biological process by which organisms produce organic compounds using chemical energy instead of sunlight. In the deep sea, bacteria near hydrothermal vents and cold seeps perform chemosynthesis. They oxidize chemicals like hydrogen sulfide, methane, and ammonia. The energy released powers the synthesis of organic molecules. These bacteria are primary producers, just like photosynthetic plants at the surface. But instead of using light, they use chemistry. Other organisms feed on these bacteria. Tube worms, clams, mussels, and shrimp have symbiotic relationships with chemosynthetic bacteria. The bacteria live inside their tissues, producing food. In return, the host provides a stable environment and access to chemicals. Some creatures graze on free-living bacteria that coat rocks and sediment near vents. Others filter bacteria from the water. Chemosynthetic ecosystems are rare. They exist only where chemicals seep from the seafloor, but they're significant. They show that life's energy requirements can be met in multiple ways. Sunlight is not universal. Life that feeds on chemicals, not light, expands our understanding of where life can exist, not just on Earth, but potentially on other worlds. The discovery of chemosynthesis. Before 1977, scientists believed all life on Earth ultimately depended on sunlight. Even deep-sea creatures were thought to rely on organic matter drifting down from the sunlit surface. The discovery of hydrothermal vents changed that. When scientists first observed the dense communities around the vents, they were baffled. How could so much life exist in total darkness, miles below the surface? The answer came from studying the tube worms and bacteria. Researchers found that bacteria living in the worms' tissues were converting hydrogen sulfide into energy. This was chemosynthesis. The discovery had profound implications. It meant that ecosystems could exist entirely independent of the sun. It expanded the definition of habitable environments. If life could thrive on Earth's seafloor using chemical energy, could it exist on other planets or moons with similar conditions? Europa, one of Jupiter's moons, has a subsurface ocean. Saturn's moon Enceladus has geysers of water. Both might have hydrothermal vents. The discovery of chemosynthesis opened the possibility that life exists beyond Earth, in environments we'd previously considered lifeless. It was one of the most important biological discoveries of the 20th century, the hidden ecosystems of the ocean floor. Most of the ocean floor is barren, flat sediment, sparse life, but in certain places, hidden ecosystems thrive. Hydrothermal vents are one example. Cold seeps are another. Cold seeps occur where methane and other hydrocarbons leak from the seafloor. The seepage is slow and steady. Chemosynthetic bacteria consume the methane. Around the seeps, communities of clams, mussels, and tube worms flourish. Whale falls are another hidden ecosystem. When a whale dies and sinks to the seafloor, it becomes a bonanza of food. Hagfish, sharks, and crabs strip the flesh. Polychaete worms colonize the bones. Bacteria break down the lipids in the bones over decades. A single whale fall can support a community for 50 years or more. Sunken wood also creates ecosystems. Shipwrecks, driftwood. The wood provides food for specialized bacteria and shipworms. These hidden ecosystems are scattered across the ocean floor. They're temporary, patchy, and difficult to find, but they're crucial. They provide oases of life in a vast desert. They show that the ocean floor is not uniform. It's a mosaic of microhabitats, each supporting unique communities. The superheated black smokers. Black smokers are the most dramatic hydrothermal vents. They emit water at temperatures exceeding 400 degrees Celsius. The water is so hot that it would instantly boil at the surface, but at the immense pressure of the deep sea, it remains liquid. The water is black because it's filled with dissolved minerals, sulfides, iron, copper, zinc. When this superheated water meets the frigid seawater, the minerals precipitate, forming clouds of black particles. Over time, the minerals build chimneys. The chimneys grow taller, sometimes reaching 20 meters or more. Black smokers are hostile environments. The water is toxic. The temperature is extreme. Yet life clusters around them. The key is that the water mixes with seawater quickly, creating gradients. A few centimeters from the vent, conditions are tolerable. Bacteria coat the rocks. Tube worms anchor nearby. Crabs and shrimp navigate the edges. The superheated black smokers are geological marvels and biological hotspots. They're places where Earth's interior meets the ocean, where chemistry meets biology. They're windows into the planet's deep processes, and they remind us that life can flourish at the edge of extremes. The cold seeps that nurture life. Cold seeps are different from hydrothermal vents. They don't emit superheated water. Instead, they're places where methane, hydrogen sulfide, and other hydrocarbons slowly leak from the seafloor. The seepage can last for centuries. The fluids are cold, hence the name, but they're rich in chemicals. Chemosynthetic bacteria thrive on these chemicals. They form thick mats on the seafloor. Clams and mussels burrow into the sediment, housing bacteria in their tissues. Tube worms colonize the area. Cold seeps support diverse communities. They're less dramatic than black smokers, but they're more stable. Vents can shut off suddenly. Seeps persist for much longer. This stability allows communities to develop and mature. Cold seeps are found on continental margins, often associated with oil and gas deposits. They're common in the Gulf of Mexico, off the coast of Japan, and in other regions. The cold seeps that nurture life are reminders that ecosystems can form around slow, steady processes. Not everything in nature is violent or sudden. Sometimes, life builds communities around quiet, persistent flows. The seeps are proof that patience, in nature as in life, can be a successful strategy. The giants of the deep. The deep sea is home to some of the ocean's largest creatures, not in number, but in size. The giant squid, Architeuthis ducks, can grow to over 13 meters long. It has the largest eyes of any animal, up to 30 centimeters in diameter. These enormous eyes capture every photon of light in the darkness. The colossal squid, Mesonicoteuthis hamiltoni, is even larger. It can weigh up to 500 kilograms. Its tentacles are armed with rotating hooks. It's a formidable predator. The giant oarfish, reaching lengths of 11 meters, is the world's longest bony fish. It's rarely seen, spending most of its life in deep waters. When it appears near the surface, it's often sick or dying. The Greenland shark grows slowly, but can reach lengths of 7 meters. It lives for over 400 years, making it one of the longest-lived vertebrates. These giants of the deep are elusive. They're rarely encountered. Most of what we know comes from dead specimens, washed ashore or caught in nets. Living, healthy giants in their natural habitat remain largely unseen, but their existence reminds us that the deep is not just a world of small, delicate creatures. It's also home to leviathans. The elusive giant squid. For centuries, the giant squid was legend. Sailors told stories of kraken, enormous tentacled monsters that dragged ships to the bottom. These tales were dismissed as myth, but they had a basis in truth. Giant squid exist. They can grow to over 13 meters long, with tentacles longer than a bus. They have eyes the size of dinner plates. They're apex predators, hunting fish and other squid in the deep. For centuries, we only knew them from carcasses washed ashore or found in the stomachs of sperm whales. No one had seen a living giant squid in its natural habitat. That changed in 2004, when Japanese researchers captured the first photographs of a live giant squid in the wild. In 2012, they filmed one for the first time. The footage revealed a creature that was graceful, intelligent, and powerful. The elusive giant squid is no longer a myth, but it remains mysterious. We don't know how many exist. We don't know their full range or behavior. We've only glimpsed them briefly. The giant squid reminds us that even in the 21st century, Earth still holds secrets. There are creatures we've barely seen, creatures that live entire lives in the deep, hidden from human eyes. The enormous colossal squid, The colossal squid is larger and heavier than the giant squid, though perhaps not as long. It's found in the deep waters around Antarctica. It has a massive, robust body. Its tentacles are shorter than the giant squid's, but armed with sharp, rotating hooks. These hooks swivel, allowing the squid to grip struggling prey. The colossal squid's eyes are enormous, the largest of any animal. They're adapted to see in near total darkness, detecting the faint bioluminescence of prey. The squid itself produces light, using photophores on its body. This may serve to startle predators or communicate with others of its species. Colossal squid are rare. Only a few specimens have been studied, most found in the stomachs of sperm whales or caught by fishing vessels. In 2007, a colossal squid weighing nearly 500 kilograms was caught off Antarctica. It was frozen and studied by scientists in New Zealand. The enormous colossal squid is a reminder that the Southern Ocean's depths are poorly explored. What other giants lurk there, unseen? What other species await discovery? The colossal squid is known, but barely. It remains one of the ocean's great enigmas. The deep-sea sharks. Sharks are not just surface predators. Many species live in the deep. The goblin shark, frilled shark, and six-gill shark all inhabit depths below 200 meters. These sharks are ancient, with body plans that have changed little over millions of years. The Greenland shark lives in the Arctic, at depths up to 2,200 meters. It grows slowly, living for over 400 years. It's the longest-lived vertebrate known. It feeds on fish, seals, and carrion. Its flesh contains toxins that must be treated before it's safe to eat. The Portuguese dogfish and the velvet belly lantern shark are small, deep-sea sharks that glow with bioluminescence. They use light for camouflage and communication. Deep-sea sharks are slow-moving, energy-efficient hunters. They patrol the darkness, detecting prey through electroreception and scent. They reproduce slowly, often taking decades to reach maturity. This makes them vulnerable to overfishing. The deep-sea sharks are survivors. They've thrived for hundreds of millions of years, but human activity threatens them. Many species are caught as bycatch or targeted for their liver oil. Protecting them requires understanding their role in deep-sea ecosystems. They're apex predators, maintaining balance in a fragile environment. The ancient coelacanth returns. The coelacanth was thought to be extinct. Fossils showed it thrived over 400 million years ago, then disappeared from the record around 66 million years ago. It was a relic of the age of dinosaurs, or so scientists believed. In 1938, a fisherman off the coast of South Africa caught a strange fish. It was large, with lobed fins and thick scales. A local museum curator recognized it as a coelacanth. The scientific community was stunned. A living fossil, a creature unchanged for millions of years. Since then, coelacanths have been found in deep waters off Africa and Indonesia. They live at depths of 100 to 700 meters, in underwater caves and rocky slopes. They move slowly, using their lobed fins to walk along the seafloor. Coelacanths are rare. Populations are small. They reproduce slowly, giving birth to live young after a gestation period of over a year. The ancient coelacanth's return taught scientists humility. Life can persist in hidden places for millions of years, undetected. It showed that the deep sea might harbor other extinct species, quietly surviving. The coelacanth is a bridge between past and present, a reminder that the ocean keeps secrets for a very long time. The mysterious goblin shark. The goblin shark is one of the strangest sharks in the ocean. It lives at depths of 200 to 1,300 meters. It has a long, flattened snout, pinkish-gray skin, small eyes, and a jaw that extends forward to snatch prey. When hunting, the goblin shark's jaw shoots out from its mouth, grabbing fish or squid in a fraction of a second. The mechanism is called jaw protrusion, and it's remarkably effective. The goblin shark is rarely seen. Most specimens are caught accidentally by deep-sea fishing vessels. It's found in scattered locations around the world, off Japan, Australia, the Atlantic coast. Its global distribution suggests it's more common than we realize, just well hidden. The goblin shark is a slow-moving ambush predator. It drifts through the water, using electroreceptors in its snout to detect prey. When something edible comes close, the jaw snaps out. The mysterious goblin shark is not dangerous to humans. We rarely encounter it. It lives too deep, but it represents the strangeness of deep-sea life. Evolution has sculpted it into a form unlike any surface shark. It's alien, beautiful in its own way. A reminder that the deep rewrites the rules of what a shark should be. The sleeper sharks of the Arctic, the Greenland shark, and the Pacific sleeper shark are apex predators of polar deep waters. They move slowly, conserving energy in the cold. The Greenland shark is the slowest swimming shark, cruising at less than 1 kilometer per hour, yet it's a successful predator. How? It hunts sleeping or slow-moving prey. Seals, fish, squid. It ambushes them in the darkness. The Greenland shark lives for over 400 years. It doesn't reach sexual maturity until around 150 years old. Its lifespan is the longest of any vertebrate. Why it lives so long is unclear. The cold slows its metabolism. Its tissues contain antifreeze compounds. It ages at a glacial pace. The Pacific sleeper shark is found in deep waters of the North Pacific. It's similar to the Greenland shark in size and behavior. Both species have small eyes, often clouded by parasites. Vision is not their primary sense. They rely on smell and electroreception. The sleeper sharks of the Arctic are ghosts, silent, slow, ancient. They patrol the deep, unseen and unnoticed. They've been doing so for centuries, and they'll likely continue for centuries more. The longevity of deep creatures. Life in the deep moves slowly. Growth is slow, reproduction is slow, and lifespans are often extraordinarily long. The Greenland shark lives over 400 years. The orange ruffy, a deep-sea fish, can live over 150 years. Some deep-sea corals are thousands of years old. One black coral colony was dated to over 4,000 years. Why do deep-sea creatures live so long? The cold is part of the answer. Cold temperatures slow metabolic rates. Chemical reactions occur more slowly. Cells age more slowly. Food scarcity also plays a role. In an environment where food is rare, slow growth and long life are advantageous. A creature can wait years for the right opportunity to reproduce. There's no rush. Longevity in the deep is a survival strategy. It allows creatures to outlast competitors, to reproduce multiple times over centuries, to survive when conditions are poor. The longevity of deep creatures challenges our assumptions about aging. On land, most animals live decades at most. In the deep, centuries are common. Time moves differently there, and life, patient and persistent, endures. The slow rhythm of life below. In the deep, everything happens slowly. A fish might grow a few millimeters per year. A coral might add a layer of skeleton thinner than paper. Predators wait days or weeks between meals. Reproduction occurs once every few years. Eggs take months to hatch. Larvae drift for months before settling. The slow rhythm is imposed by the environment. Food is scarce. Energy must be conserved. There's no benefit to rushing. In fact, rushing wastes energy. Better to drift, to wait, to move only when necessary. This slowness is difficult for humans to grasp. We live fast. We measure time in hours and days. But in the deep, time is measured in seasons, years, decades. A human lifetime is a brief flicker. The slow rhythm of life below is not laziness. It's efficiency. It's adaptation to an environment that rewards patience. In the deep, the slow survive. The fast starve. It's a different calculus of life, one where time is abundant and energy is precious. The sounds of the deep sea. The deep sea is quieter than the surface, but it's not silent. Sound travels well in water. much better than in air. Whales sing to each other across thousands of miles. Their songs penetrate the deep. Ship engines rumble. Sonar pings echo. Even the movement of tectonic plates creates low-frequency sounds. Some deep-sea creatures produce sounds. Fish grind their teeth or vibrate their swim bladders. Snapping shrimp create cavitation bubbles that collapse with a sharp crack. Marine mammals use clicks for echolocation. Submarines detect these sounds with hydrophones. Scientists use underwater microphones to study marine life. They've discovered that the ocean is filled with sounds we can't hear, infrasound and ultrasound beyond human perception. The sounds of the deep sea are subtle. A distant hum, a faint click, a low moan, but they're there, and they carry information. Whales navigate by sound. Fish locate prey. Submarines hide in the noise. The deep is not silent. It's a world of whispers, and those who listen carefully can hear the ocean speaking. Whales singing in the distance. Whales are creatures of the deep, even though they breathe air. Sperm whales dive over 2,000 meters to hunt giant squid. Blue whales, the largest animals ever to exist, migrate through deep ocean basins, and all whales sing. Their songs are hauntingly beautiful. Humpback whales produce complex melodies that can last for hours. Each population has its own song, which evolves over time. The purpose is not fully understood. It may be mating displays. It may be communication. The songs travel vast distances. A whale's call can be heard hundreds or even thousands of kilometers away. The deep ocean acts as a waveguide, channeling sound efficiently. Whales use this to stay in contact across empty expanses. Sperm whales produce powerful clicks for echolocation. These clicks are among the loudest sounds produced by any animal. They use them to stun prey and navigate in darkness. Whales singing in the distance are a reminder that the deep is connected. A whale in the Atlantic can be heard by another whale thousands of miles away. The ocean is vast, but sound bridges the distance. The deep is lonely, but not silent. The whales sing. The secrets carried by ocean currents. Ocean currents connect the surface to the deep. They carry nutrients, oxygen, and heat. They transport larvae and organic matter. Without currents, the deep would be even more lifeless. Thermohaline circulation, sometimes called the ocean conveyor belt, is a global system of currents driven by temperature and salinity differences. Cold, salty water sinks in the polar regions, flowing along the seafloor toward the equator. Warm surface water flows toward the poles to replace it. This circulation takes centuries to complete a full loop. Currents bring oxygen to the deep. Without it, most life would suffocate. They also carry nutrients from the deep to the surface, fueling phytoplankton blooms. Upwelling zones, where deep water rises to the surface, are among the most productive areas of the ocean. Currents also carry pollutants, plastic particles, chemical contaminants. Even in the deepest trenches, scientists have found traces of human activity. The secrets carried by ocean currents are not all natural. Some are reminders that the ocean is not isolated from human impact. The hidden mountains beneath the waves. The ocean floor is mountainous. The mid-ocean ridge system is the longest mountain range on Earth, over 65,000 kilometers long. It winds through the Atlantic, Pacific, Indian, and Southern Oceans. These mountains are volcanic, formed by seafloor spreading. Magma rises from the mantle, creating new crust. The ridges mark the boundaries between tectonic plates. They're not smooth, they're jagged, broken by faults and fractures. Valleys called rift valleys run along the crests. Hydrothermal vents are common along the ridges. Seamounts are underwater mountains that don't reach the surface. There are over 100,000 seamounts in the ocean. Some are extinct volcanoes, others are still active. Seamounts create habitat. Currents flowing over them bring nutrients. Fish gather. Corals grow. The hidden mountains beneath the waves are largely unmapped. We know their rough locations, but not their details. High-resolution mapping is expensive and time-consuming, but it's important. These mountains influence ocean currents, climate, and ecosystems. The hidden mountains are not just features of the seafloor, they're shapers of the ocean itself.